Thanks everyone for your attendance. And then I am going to jump somehow into another aspect that we realized that it was important in the definition of these case studies and then solutions of some of the alternatives for these case studies. That my colleagues have already explained, we started by doing some certain surveys during a webinar, a workshop, in fact, that it happened in Bern. So I am going to talk about those motivations that lead to the development of this tool. First, I just would like to give you a first outline of this. Let me just take not the pen, maybe the highlighter. Yeah, the laser pointer. So we will start describing the objectives and the relevance of developing these sort of tools for these kind of projects, how the product profile, so how the tool has been conceived from the feedback of the attendance of that workshop that I mentioned, the tool workflow for the process integration and the pinch analysis. I will discuss, so here I have a type, sorry, Osmos algorithm, which is let's say the core of the optimization process inside of the tool. The data input interfaces in the way that we are going to input the data, either Excel based or the flexible fashion that we are going to use for injecting data in the tool. The heat pump superstructure, because it's a very important concept in the tool, in which, as you will see, many details of the heat pump can be inputted as data for setting, tuning the parameters of the heat pump, and even doing sensitivity analysis. There was a simplified good that has been developed because of the request of the attendees as well of this workshop and many other users that are not familiar with coding. Typical results that the tool reports and how it could be validated. So I will go quickly through some examples of use because you have seen already many of those discussions in the previous presentations and conclusion and path forward. So cannot click. Maybe it's because I need to remove the eraser, the pointer. Okay. So the objective of this development of the tool is to introduce this support tool, support decision tool for designing and also integrating high temperature heat pumps and as well conventional heat pumps and many other technologies into industrial processes, to have an open source tool that is flexible. It can allows, it allows to have modeling, analysis, but also documentation. This is very important, of the energy integration results of these industrial processes. In order to what? To inform the end users, technicians, managerial, engineers, society in general, about the importance and benefits of applying these process integration techniques into industrial processes, including or not heat pumps. So it could be one of the solutions of the integration analysis. But which are the challenges, or why is it so relevant to have this sort of tools? It's because there is an increasing number of technological options. So you have heard about mechanical vapor recompressors, you can hear about the heat pumps, but also already in the enterprises you have biomass boilers, natural gas boilers, electrical heaters. So we need to take into account all of those technologies to make a comparative analysis for this, emphasizing in the easiness of the visualization. And there is a lack of intuitive and open source tools. So there are many paywall tools, but we would like to have open source tools that can be deployed to do fast and accurate pinch analysis. So the product profile, it was based in the roundtables of the workshops. So there were a survey in which we wanted to know how to design and transfer this technology, because many attendees of that workshop wanted to generate and evaluate options. So they wanted to know if, even if it's optimal or not, different options that they have with variable conditions and competing technologies, so basically trade-offs, determine if there are integration errors, so checking if they have misplaced utilities, what is the pinch point, etc. But also an improvement of the data management. So they wanted to centralize, have an updatable and then trackable access to the technical data. So if they have a data that has changed, then everyone can see it in real life has changed, because it will be in a centralized database. And still wanting to keep some of the familiarity with the office utilities that they have, like Excel, because it will ease the opt-in of the users into those technologies. Then it will enable the flexibility as well to communicate integrate with in-house software and other simulation software. So they want something that is automatic, allows to do a lot of tasks, but everything in one place, so that they don't need to open one file and then copy paste into a PowerPoint. They will have everything in one report. The concerns, of course, are the software licenses, because they know that this limited accessibility to algorithms of paywall softwares, and also that reduce the flexibility and cost. I mean, if the heat pump already generate a lot of cost, they don't want to pay too much for doing this preliminary analysis. So the web-friendly reporting formats, in the case of the HTML files that are easily deployed online, that can be seen with any web browser, are one of the objectives of this development. But then there are still some questions regarding where to host the servers or do local executions. That will be discussed later. So which is the workflow of the tool that we have developed? Initially, we start by using the data defined by the user, by the enterprises, the audits in an Excel template, but it can be also inputted directly by coding or using flow sheeting software. So you can use Aspen or CoolProp to determine thermodynamic properties. And then we use this Osmos platform, that is a platform that has been developed in EPFL for solving mixed integer linear programming. So this is basically for optimizing the integration of those systems by minimizing the operating costs, the impact, the environmental impact, etc. So it consists of a front end that it sends the data to the Osmos engine that does the execution of the optimization problem and then solves this synthesis problem. It produces an output file in a JSON format that is easily to be accessed by any open source utility, like or library languages such as Python or whatsoever. And then you can, with this information, to visualize and calculate KPIs. So when you generate that report, you can have a feedback loop, because you will have an HTML report that summarizes everything. You're supposed to summarize everything: the problem definition, the assumptions, the results with the tables. It's structured, and you can share it because it's basically an HTML file on a folder. You can share zip it and folder to your manager. It's important because at the end you can have a feedback loop. You can always change the parameters and do a feedback loop, inject more data from the industry, and then you can determine which are the pinch points, penalize heat exchangers. So you can take actions at the end, and then you can refine the superstructure utility, superstructure of heat pump utility, just to know which is the effect, the what is, if you change the parameters of those heat pumps. I am not going to enter too much into detail because this could take a lot of time. Go into the details of the algorithm in the backend that is in the Osmos engine, but this is just for you to know that is a multi-objective optimization software that it has been via the R Markdown environment transformed into a web-based decision tool. As I say, is based in the MIL paradigms, and then it can help you to select the optimal energy technologies and utility systems. This by minimizing some of the KPIs that you can choose. The superstructure, of course, it needs to have all of the competent utilities. It needs to have the furnace, electrical heaters. We need to be transparent, and then in that way we can be more convincing if the heat pumps is or not the best solution. So it can integrate several tools, as I say, and several visualization routines. So which are the data input interfaces? So when we want to generate this pinch analysis report, it will require, of course, many of the data of the mass flow, thermodynamic properties, the supply and target temperatures you have seen in the previous presentations. And then all of the input, it can be done. You can do it manual insertion. So directly in the code, we can discuss that later. I can show you. You can manually insert the hot and cold streams using flexible code, but you can import it also from Excel, or you can take flow sheeting software. So the data can be also eventually, when the enterprise is interested, collected in an open platform communication acquisition program, and then transform it into JSON and CSV, and later on, then you can use the same workflow that I have described before. So the Excel-based data input is as I shown here. So probably I will need to jump into this. So let me go here to show you how it can be injected the data. So basically, you will have a template in Excel with 4 main tabs. I am showing them here quickly, in which you will be able to define, if you have like mass streams, you will be able to define which are those mass, if it's natural gas, if it's milk, if it's air. In this case, we are going to focus only in the heat stream. So what it will be interesting is to define that you will have one unit. In this case, I am going to call it the clean in place. That is the process that you have in your enterprise, and you will be able to define certain parameters, most of them related with the bounds of this system. If it has some operating costs, I am just putting here some dummy values, but it will require like values that are defined like project specific. On some mass streams, but I will focus especially in the part of how to inject them into this specific unit that I have defined as the cleaning in place, some of the parameters that are required for a basic pinch analysis. So the T in, so the T source, the T out, in this case, the target, you will have like the difference in the enthalpy, so what it will represent the heat exchange. So if you have hot streams, you have cold streams, they will be represented, they will be characterized by the temperatures, but also by the heat. There are some specific parameters that are very important for the pinch analysis. That is the delta T mean contribution, but also the heat transfer coefficient. So this is important because at the end, you will be able to import this file with all of these tabs and generate, as I am going to show later, an energy technology that represents the processes that is inside of your plant. So I am going to go back here, switch to this. And then, as I have shown, you have this Excel-based data input in which you will be able to define your connections, so ensure that the mass and energy balances are satisfied. You will be able to define also costs of the grids in this layers definition. You will be able to define one or multiple processes or utility units. I will show you later how it's seen in the software, because we would like to put into competition the heat pumps with the other boilers and alternative technologies. We need to define the mass streams in the case that you would like to do not only the heat integration, but also the mass integration. And then it will require the knowledge of the material and electricity that is flowing through these connections between the energy technologies. And the heat streams, that, as I say, is the most important when you want to do like simple, at the beginning, simple heat integration analysis. So it will require basically temperatures and heating and cooling duties. So you can do it. I just will go relatively quickly through this because it's equivalent to the previous one, just that you can do it directly in the backend, so in the programming mode of the tool. So you will be able to define parameters, you will be able to calculate parameters, you will be able to define the streams in the same way that in Excel, but directly in the code. So it's the flexible way in which you will be able to inject temperatures, enthalpies, you will be able to inject other parameters, mass streams, energy streams, and at the end you will be able to generate a project, solve the project for different energy technologies. So you can consider cooling water, you can consider heat pumps, cogeneration systems, and of course your process. But it's something that for this webinar is very important, is to define the heat pump superstructure, so the importance of the heat pump superstructure. Because in this case, as we know, the heat pumps, it may consist of several levels of temperatures and of course pressures, in which we will have condenser heads and evaporator heads. So if we consider a superstructure, I am not going to go into the very much details, but all of the possible combinations of pressures and temperatures that you are going to suggest to integrate these heat pump headers and condensers and evaporators and the fluids. So you can give a lot of those parameters and let the tool to decide which of those headers, so which of those layers of temperatures and pressures are going to be selected, which are the most suitable, and also which are the best fluids for those specific applications. So it's a core element in there. So you will be able to define candidate fluid lists. So you will say that you will require to use some HFOs or some ammonia, water, organic. Even you can put some of the forbidden refrigerants just to do some what-if analysis. You will be able then to define the temperature level, some superheating and some cooling temperatures out of the headers of the evaporation and condensation, minimum temperature difference contribution, and other economic parameters and bounding parameters that you can read later on when I share with you the tool. It's also interesting to know that we have developed a database of technologies that you can download it freely in this website, in GitLab, because there are many other models of technologies, not just heat pumps, but electrical heaters, and there are also the carbonization technologies that we have injected into this tool, so that someone that is not very familiar with many models and competing technologies can go and then just by right-clicking in the tool, you will be able to inject it into to the heat pump technologies. So vendor technologies as well, all of the data that came from the Annex 58 database, it has been also injected there, and done some storage systems that are in work in progress. So I am going to show you quickly how it looks like when you want to use this tool in the simplified GUI, because you will be able to download it as a Python library, and then you will execute it, and at the end you will arrive into the following layout. So you will be able, for instance, to import Excel files. So you can import an Excel file, and the data, as I showed you in the previous template, it will appear in this tool. I am going to just quickly go afterwards through the tool to see how I can import these files. But you can import Excel files that have all of the data of the industrial process that you are analyzing. You can create other energy technologies. You can input heat pumps, steam networks. You can generate your own like tailor-made ET, so energy technology. But you will be also able to import it from the database that I mentioned before. So you can import some energy technologies. At the end, the idea is to generate a superstructure of candidate utilities and industrial processes. So here you can see an example of cleaning in place and technologies that can supply this cleaning in place system. And you will then be able to run this optimization problem and define which are the temperature levels of the heat pump, but as well which are the sizes of the cooling water. You would like to minimize the cooling water because you want to use this heat, in fact, to supply the heat at high temperatures by using the heat pump. So this is, of course, always an optimization problem that has a lot of trade-offs related to the minimization of the environmental impact by rejecting waste heat, but also minimizing the fuel consumption, but maximizing the use of this waste heat inside of the plant using heat pumps. So the import of the Excel file is relatively easy. You just say that you want to import a certain file, the ET Excel file that I have shown you before, and then at the end it will appear in your superstructure database here, in which you will have all of the information summarized about that specific ET. But then you will be able, of course, to include the cooling water, and then you will be able to document. So you can write some of the assumptions that you have assumed for this specific utility. You can say my cooling water. You can describe it just if you want to appear it in the report in a nicer way. But you can connect as well the ET, the cooling water, with the other systems because it will require electricity and make cold water. So you can also link your ETs, your different cooling waters, clean in place, heat pumps, and market by using some layers. And you can define as well then for the case of the different ETs, you can define then its characteristic temperatures, heat exchanges, mass streams. So you can adapt it because, in fact, if you see the heat pump, you will have access of all of the data of the parameters of the heat pump. So you can actually you can click on it and you can change it. So you can edit those parameters in this simplified GUI. At the end, you will define them. Since you have this superstructure, you will be able to define a project in which the superstructure that considers, you can see here, the cleaning in place, the cooling water, the heat pumps, superstructure, the market. You will be able to define a project. I am calling it here cleaning in place project, where in which I would like to determine which is the minimum energy requirement. So this minimum energy requirement here, you can call it MER, it will determine which is the minimum heating, the minimum cooling, and it will be able to plot the composite curve and the grand composite curve. So you will run the Osmos tool, and you will be able then to have some results and compare them in terms of energy consumption, which is the breakdown of the cost, and how does it look like the composite curves. So let me go very quickly to show you how it looks the tool. So this is the way how it looks the tool. This is how I was mentioning that you are able to import the Excel file. So you can choose the Excel file. If you allow me to go here, you can say I want to import this Excel file, and this is the Excel file that appears here later on. You will be able to go to this unit, and you can see that all of the parameters are here. And as I tell you, can, if you want to afterwards change the values of the parameters, you can change the values of the parameters. You can go through the cooling water, see some of the documentation of the cooling water, see how it has been defined, all of the streams of the cooling water. In this case, we are defining basically the heat stream that is going to receive the heat that is rejected from the process, as well as the heat pump system. So you are able to see all of the parameters that are injected into the heat pump. You can change it, you can define other parameters as well, and then add some comments to document it in your system. So when you run it, so when I say that you can run it, you are able to define here the name of your project. You are able to define here the specific objective, for instance, the total cost, which are the technologies that will be involved in this optimization, change the operating cost. You can change the solvers that you want to use. This is probably a little bit advanced for the people that wants to change the solver that they are using, and then define which are the KPIs that are going to show. And then you can run, when you run it, it can take some time, so I will just show you which are the results. You will have results about the composite cores in the case of the MER optimization, but you can also have results for when you close the balance by using cooling water, heat pumps, and when you are optimizing with the total cost, you will have other results that I am going to discuss later on. So this is how it looks, the tool. As I say, you can have you can add technologies in databases. You can create your own tailor-made model. So this will require a very hands-on session, a very long session to know how to use it. I am just showing you what it can do. And then at the end, you will have an HTML-based report that it will have like a nice summary of all of the assumptions, documentations, results, but also it will have the course that you will see here. So I will show you here how does it look like. For instance, in this report, you can have at the end an HTML report, so a web-based report in which you will have your introduction, you will define your problem, you will define how does it look like, the cleaning in place, which are the assumptions that you have had there, which are all of the utilities that you have considered to compete there. And at the end, let me just go through the results. You will have a discussion about how it looks like the composite curves, how it looks like the grand composite curves, which are some of the indicators at the end, the minimum energy requirements and minimum cooling requirements, and which is, of course, if you go to the optimization on the total cost, you will have other KPIs. So it will have like analysis, how does it look like the integrated curves, how does it look like the integrated curves when you are using fossil resources, also how does it look like the integrated curves when you are using heat pumps. So when you reduce the reversibilities of the system, you can compare this sort of KPIs, operational expenditures, capital expenditures, impact. You will be able also to do breakdowns of the operating costs, some visualization of the process flows, which are some of the flows inside of the analysis that you have done. So environmental emissions, natural gas consumptions, electricity consumptions, etc. So also in the case when you are optimizing by integrating heat pumps, you will be able to have some of the details in terms of the evaporation heat, the condenser heat, which are the compression powers, calculate some of the cups, which of the fluids of the list of the fluids that I have shown you before, and which of the levels of compression has been activated, and some heat exchanger network details that is also reported by the Osmos tool. So I will go quickly, and sorry if I am taking a little bit longer, I will go quickly to summarize which are the typical results that it can produce. So as you can see here, minimum energy requirements, pinch point, graphical representation of hot and cold composite curves, grand composite curves, compression powers, mass and energy flows, and other economic KPIs. So I am going to go relatively quickly to these examples of use because you have already heard about them in the previous presentations. But basically, with the tool, you can do some analysis, like what if analysis. You can change some of those assumptions that you have had for the electricity cost, the tax, the yearly operating hours, annualization rate factors. The boiler lower heating values if you are using biomass, if you are using natural gas, emissions, indirect emissions, and other parameters. With that, we can go like into an analysis by using the tool of the Weir ultrafiltration rate drying, that is the taxotherm, and the cleaning in place system that you have already seen in the previous analysis. So the tool, as you have seen, it can define them for you that there is availability of waste heat that is around 1,000 and 2,000 kilowatts of heat, and it can show you which are the levels at which they are available. So you can see that are more or less available at between 45 and 25 degrees in this case of the curve. So one is for the wide drying, another is for the cleaning place. It could be used to feed then the heat pump, this waste heat, to heat pump or to pump heat at higher levels, in this case between 90 and 120 degrees. And then, as you can see, there is the heat pumps are potentially favorable because at some point you will be able to reduce the cooling and reduce also the natural gas consumption or biomass consumption for the heating. But you need to combine multi-stage and heat cascade heat pumps in some cases because of the large temperature lead. So these are some of the results, as I have shown you before in the HTML report, in which you can see the composite curves when they are balanced. So comparing, in this case, for the wide drying, when you have the consumption of natural gas, you have a very large driving force, which increases here the reversibilities of the problem. You can see how it can be reduced, all of this area, this gray area that represents the reversibility of the exergy destruction of the process, by installing heat pumps. So basically, or in layman words, you will say they're approaching the two curves of the utility supply and the process, that in this case is the blue curve. You can also have then the economic indicators that I have shown you before, the economic indicators, the impact indicators. You can have the details of the heat pumps and the streams. I have shown you in the HTML before. For the cleaning place as well, is notable how you can reduce the reversibilities and also how you can reduce the emissions of those systems. So I will just go by some conclusions in here, only just to show you that by using this tool, visually representing and documenting the results, you are able to conclude that combustion to only preheat water to 90 to 440 is an avoidable inefficiency. It's a large energy destruction that could be avoided. Also, the systems, they require large cooling. So what it tells us then that is an untapped waste heat recovery potential, because we can recover waste heat from the refrigeration condensers, but also from the water cooling. And then we need to electrify, of course, but then for electrifying, we will need to, let's say, make greener as well the electricity. For the well drying takeaways and the cleaning place takeaways, you can see, and is also consistent with the previous results of the other presentations, we have emission reductions that can go from 80 to 90%, just by reducing the cooling, the cooling needs, but also capitalizing these cooling needs to supply this waste heat at higher temperatures. You can have economic savings that can be reported also by the tool, halving the cost sometimes, or just by 1/3. But you may have also economic savings that it can depend, of course, in how I are assuming the capex and the opex of the systems. So we can see that actually these two specific processes that we have shown by using the tool are favorable, preliminarily favorable, because of the temperature levels and the amount of waste heat that we have. But there is a competition of the utility system that we need to show to convince actually managers and other technicians to use these tools, to use heat pumps, because we know that there is a competition that this requires a tool to systematically compare the performance of alternative technologies. So we need to automate that those computational calculations and reports. So we need to present a way of reporting and comparing in a visual way. But at the end, everything will be just for helping, because we are not going to give which is the right let's say approach, which are going to show which are the scenarios that they have available, which are the technologies that they have available, and depending on that, they will be able to determine if the CO2 task, if the internal policies will allow to offset then the initial investments, if they are let's say in agreement with the challenges related to the reliability, space budget, and maintainability of these technologies that are of course not analyzed in this tool, but it could be included later on. But the preliminary analyses are clear, and then we have waste heat that needs to be recovered, and those tools and the visualization of this energy integration analysis are the way to convince in a graphical way that we have this potential and that we can start doing some more in detail analysis. But there are some complications, let's say issues that needs to be still addressed, and is the massive deployment of these tools. because it required training programs. Nicole, Pierre, and Cordin also mentioned it. We need training engineers. So we need these training programs, and we need a business model, because some of these tools, as we say, they are paywall. But when we go to open source tool, we will require a community that embrace these sort of projects, and it will be able then to try by helping, but having the collaboration of a community that is helping to develop and maintain the tool. So the server hosting and the confidentiality also, when the enterprises, they think that they are going to send information into an external server that is based, I don't know, in EPFL, in another institute, they will have these confidential issues that still will need to be tackled together with the partners. So future developments, I am just closing here. You will need to see then the containerization of this to be able to execute it in local servers or in EPFL servers with authentication. Some projects like in this annex, but other tasks and masters in advanced studies that we have in EPFL, we have been already using partially this tool, and then it has been validated by the use of these partners in the industrial field. Some messages and lessons that we will discuss later on with the intervention of the other industrial partners. I just would like to acknowledge the Swiss Federal Office of Energy, show some of the faces behind of this development. So you can see that it's composed of chemical, mechanical engineers, some IT specialists, and also another people in the research group that have helped in validating, using it, presenting, proposing some improvements as well. Some references and publications that we have done, and I am open for questions later on. I hopefully has not surpassed all of the time that I have. Thank you, Cordin. The floor is yours.